Yeah, thank you very much. First, I would like to thank the organizers for the opportunity to speak here and to interact with the colleagues at this wonderful conference. So I would like to talk about topological aspects of switching in magnets, and in particular in spiral magnets switching with electric field. And so this work was done in collaboration with Professor Nagalosa from RIKEN, Pimena from Vienna, and group members Louis Panet, Francesco Fagetti, and Margarita Parodi, who is also here and presented a poster yesterday. So the first part of the talk is topological switching process. So we would like to store lots of information for all kinds of reasons, and basically the information is currently stored in these big data centers, and the amount of energy that's required for storage is basically exploding. In the US data centers are using about 2% of all the generated electricity. And one of the culprits is that we are using magnetic hard drives where the magnetic fields cannot be localized efficiently, and so the bits cannot be made smaller, and also the currents that are basically used in miniature electromagnets to switch the bits are leading to dissipation. And so typical switching mechanism in a ferroic device looks like this. So there is a double wall potential that mimics basically mimic two possible domains with spin up and down. And when you are applying external bias, external field, magnetic field or electric, you are basically lowering one of the minima. And so you have to nucleate a small domain here and then propagate the domain wall through that sample. And the domain wall hits all kinds of disorder and dislocations and impurities and whatnot, and that leads to the hysteresis. The area of the hysteresis loop gives the energy that's required for the switching cycle, and so that's the heating that we would like to avoid. And so I will discuss the material where it seems that such heating may be avoided. So basically the idea basically is demonstrated here. Here I show the potential energy surface of this material. So the material is gadolinium manganese 205. It has this manganese chains that I showed here in blue. And basically, when the magnetic field is applied to this material between something like 4 Tesla and 4.6 Tesla, the evolution of the potential energy surface as a function of field is shown here. So at the lowest field, there are two minima corresponding to states 1 and 3. And when the magnetic field is increased, let's stay in this state. As the magnetic field is increased, basically the barrier on the right disappears, and the state here moves to this state 4. Then the field is reduced. Now, when the field is reduced, I go to this state where the barrier on the right again disappears, and I move into state 1, and so on along the loop. So basically, instead of the need to nucleate a new state in the minimum, I can, this material gives a way to modify the potential energy surface in such a way that the state is guided around the loop, not by domain nucleation, but in the bulk. So at this point, basically, there is this spinodal decay. There is no way for this state to stay here. It will be forced to go to state 1 potentially in the bulk. Mm-hmm. Mm-hmm.
Two questions. So here on the purple curve, when it falls down, you still lose energy, right? So it has to dissipate shortly, right?
Yeah, right. So indeed, in this scenario, yes, but in principle, one can think of organizing the rotation of this potential energy surface. That basically, I'm deforming the potential energy surface in such a way that, this energy is not lost in the interactions with the lattice. Like, I'm not depositing it into the lattice. It's just the energy that,
more fundamentally, you're doing a trace with one parameter, right?
Mm-hmm.
If you want to do something which is non-dissipative, you need two parameters, like Taylor's fountain, right?
Yeah, right. So, yeah, exactly. So, and then basically that kind of brings us to the idea that essentially you could be changing the parameters of your potential energy surface in such a way that you would be, moving this state. So it's an improper ferroelectric. So polarization is given basically by the product of the magnetic order parameters. And so basically one could think of the situation where the minima are moved in the space, and basically the polarization up minimum becomes polarization down. And so in this case, basically I have the spins that have the winding number characterizing the, and in Pauli's pump, I have basically the Berry curvature that's basically responsible for the charge that's pumped in the cycle. And one can illustrate it in this simple situation where, in a simple tight binding model where the parameters of the model are basically controlling the heights of the minima, one can show how this charge is pumped along the line. So one can make this connection closer basically by looking at the trajectory of these order parameters in space. So basically, the first time this effect was discovered by Andrei Pimenov's group in Vienna was that basically when they apply magnetic field along A axis and measure polarization along B, they see this kind of spin-flop transition here, and polarization changes at this spin-flop. If they apply the magnetic field at minus 15 degrees to A axis, if they apply magnetic field along A axis, then polarization between this positive and negative polarization states occurs. But within this narrow kind of magic angle interval around 10 degrees, one sees this 4-state hysteresis loop. So if I'm ramping up the field, I'm going to this polarization up state, removing the field, then I go here. And basically, I did one ramp up down, I switch the polarization sign, right? Then I'm increasing polarization, increasing the magnetic field second time and removing it again, and then I switched it again. So basically this device works as a binary counter of magnetic field pulses. And so if I'm looking at the directions of spins, so here I'm basically plotting file 2, file 1, so the directions of spins in the two chains. As I'm applying the field, then basically for low angle, so for these trivial situations, for the high angle and low angle, I'm basically, file 1 is changing by pi half between pi and 1.5 pi, and here between 0.5 pi and pi, right? So that corresponds to this contractible loops here and there. But in between the two situations, I'm basically following this whole potential. This has a topology of torus because 0 is the same as 2 pi, right? And so basically I'm going around the whole of the torus. And this is this incontractable curve that's seen basically in this topological regime. Okay, so microscopically one can think of a spin-flop transition. So basically when I'm applying the magnetic field along the spins in the antiferromagnetic chain, spins can flop, left to right. So one can describe it in simple ways like this. So I have plus LZ state, let's say, and I could go to plus or minus LX. And in normal spin-flop transition, I go 50-50. But in this situation, I go around the loop. So there is a specific directionality to this. Okay, then basically, this is the mechanism that was discovered experimentally that's working at very low temperatures, right? At only 2 Kelvin, this material works because rare earth in gadolinium manganite orders at very low temperature. But it gives us the hint that maybe one could make the more interesting and also efficient potentially memory devices based on this switching. And then second part I would like to discuss also has to do with controlling the magnetic states with the electric field. So I'd like to discuss spiral magnets. One of the seminal papers in this area was the work of Kimura and colleagues in 2003, where they showed that spiral magnet induces ferroelectric polarization. We can understand it in a simple way. If I look at this piece of a spiral and do inversion in this center, spins do not change under inversion, but the sides do. And so this spin goes basically here, so it becomes counterclockwise rotating spiral instead of clockwise under inversion. And so spiral breaks inversion, and these clockwise and counterclockwise domains correspond to polarizations in opposite directions, so opposite polarization domains. So if I'm thinking of a domain wall between state like this and like that, then I can move this domain wall, this magnetic domain wall, by applying electric field. So the mechanism for this coupling is actually inverse Zawaczynski-Maria or spin current mechanism that was basically discussed by Katsura, Nagausa-Balatsky, and a number of other works from microscopic and phenomenological standpoints. And basically, it's about the Zawaczynski-Maria interaction being controlled by this bending of the bond. So by the dm vector essentially given by the vector connecting spins cross the shift of the oxygen between the transition metal ions. And so this shift of the oxygen is basically the ferroelectric polarization. So if the octahedral tilts lead to this back-out oxygens, then spiral appears due to Zawaczynski-Maria. That's seen in many materials, like bismuth ferrite is probably the most famous. But in terbium-manganite and other materials where the spiral is stabilized by competing exchange interactions, where the spiral is already stabilized, this mechanism gives off-centering of oxygens, right? So it induces polarization. And the polarization, the induced polarization will be opposite for clockwise and counterclockwise domains. Okay, well, so the typical models that one can discuss in this context are the models with competing nearest neighbor and next nearest neighbor interactions. Let's have some easy plane anisotropy and with Zawaczynski-Maria interaction that couples the spin rotation to polarizations and electric fields. I mean, one can use a more general phenomenological model, continuous model like this, and I also added a kinetic term. And so let's discuss the behavior, the domain walls in this quasi-one-dimensional model. And I'm assuming ferromagnetic interactions in the perpendicular directions. Antiferromagnetic interactions can also lead to interesting effects. So in principle, there are two ways I can create a domain wall. I can think of two types of domain walls. So type 1 domain wall, what we call type 1, is basically when spins lie in the plane. And basically with faint colors, they encode the spin rotation direction and the polarization. So here basically spins are rotating clockwise, and here staying within the plane, they change into rotating counterclockwise. And then second option is that the spin rotation plane can twist. So if the spins are rotating in this plane and then the plane twists, that also leads to the reversal of the spin rotation direction. Yeah, it's kind of similar if you think of the basically spin rotation vector, you know, that's making one the domain wall another. Right, so then basically depending on the, so it's not too easy to find this domain wall. So it turns out that in order to stabilize this domain wall, you have to have a wave vector close to 0 and reasonably large easy plane anisotropy. Then this type of wall is stabilized. And then we can also plot the winding number here, so that basically the angle, let's plot the angle that characterizes the spin direction here. So across this domain wall, basically spins are rotating clockwise and then counterclockwise. So I can represent it by this plot, right? So the domain wall is here now. Then I can do the same trick here, but here basically spins are getting vertical at some point. So the polar angle is not well defined. And as spin goes through the north pole, the phi angle basically changes by pi. And so that's corresponding to this change. So here there is basically a continuous line. right? And one cannot break it. While so it's protected by basically J1, J2. Energy to introduce a sudden twist here would be very high. While in this domain, though, no problem. I mean, twist just there is a sudden jump of the angle. That's natural. So basically, in type 2, spins can get vertical, no winding number meaningfully defined. But in the type 1, spins lie in the plane and there is a winding number. And so, well, why am I talking about winding number? What's the meaning of it? Well, so it turns out that this winding number is directly related to the ferroelectric polarization, to the integral of polarization over the whole sample. So I can basically compute this S cross nabla S, and then I get basically phi on the right minus phi on the left. So the total angle of spin rotation gives me that integral of ferroelectric polarization. That's what the uniform electric field couples to. Then the dynamics, so let's look at this type 1 ball. Basically, spins are rotating clockwise, then counterclockwise, then clockwise. So the type of dynamics that I can do not to break this curve, right? I can, for example, I can move this blue segment here in the dashed position. So you see that basically the system is characterized by these phasons, right? I cannot basically break these lines. I cannot change the Q vector. That will cost me in terms of J1, J2. But what I can do is basically move these segments up and down, right? So the system is basically dynamical variables are these phasons that are basically telling me the vertical positions of these segments, right? And if I move along this phazon, right, move from here to here, basically I'm increasing the red domain here, but increasing the blue here as well. So the total polarization changes 0. Phi 1 minus phi 3 is still the same. So basically the electric field does not induce the motion of inner domain walls. So here basically only the outer domain walls will move if the electric field is applied, because moving inner domain walls does not change the E dot P, does not change the polarization. So only changing phi 1 and phi 3, right, will lead to the change of polarization and of the P dot E term. So electric field is basically in this system, due to all this twisting happening, electric field doesn't care to change the phasons in the middle of the system. There can be any number of domain walls, but electric field only couples to the phasons of the outermost walls. And so in thermodynamic limit, there will not be any susceptibility due to walls. So if the electric field applies, all the domain walls in the bulk will not move. So there is only a surface contribution, not a bulk one. Okay, then so one can also find the velocity of these walls using Tilly equations. Or well, that are basically telling us that just like for a ball falling in the air, the velocity is controlled by the pressure that the electric field exerts versus the friction force. And here friction force is basically the Gilbert damping that's acting on all the spins. So in normal ferromagnetic domain walls, only the spins within the wall change as the wall moves. But here all the spins in the domain must move because the dynamics relies on a phazon. And so the damping force becomes proportional to the width of the outer domain. And this gives the formula for the velocity that's inversely proportional to the width of outer domain. So the velocity formula you get is something like electric field divided by Gilbert damping, width of the domain, and the wave vector of the spiral. Okay, and then another interesting, so opinion I will discuss in a moment, but basically in the type 2 walls, on the other hand, one can make always sudden jumps in the phi. And so here basically all the walls are moving due to, this is about these twisted walls, right? And so the twists can independently move, all of them. And so there is a contribution to the susceptibility in the thermodynamic limit. And velocity is independent of domain wall widths. Yeah, please.
If you were to choose your North Pole
Yeah, certainly. But in any case, this is just to say that in the type 1 wall, I will always be able to define a continuous angle, right, when the spins are lying in one plane. But when the spins are not, then through the twist, there will be always discontinuity in the phi. So I mean, in one case, I basically have this continuous winding number, and here I cannot define it well. So basically, if the spins are in the plane, there is just one angle, right? And then if they are not in the plane, then I can move the North Pole away, right, to put the singularity somewhere, but it doesn't help after all. Okay, so then some spin dynamics simulation. This is just Landau-Lifshitz-Gilbert dynamics to convince you that this kind of walls I'm going to describe, they do exist. On the left, I'm showing the polarization. So this up and down polarization domains correspond to, you know, winding clockwise and counterclockwise. And this is Fermion charge density to show that basically these objects here, they are merons. They have topological charge 1/2. Okay, so basically I start from a completely random configuration, then the domain coarsen, and domain wall like this appears. And we are studying the motion of that domain wall. So I'm showing here with all these different curves, starting from while at t equals 0, right, starting time. And as the time progresses, the spin configuration is indicated by the red curves, right? So going from violet to red. And so basically I started with a single wall here in the middle. So clockwise winding, counterclockwise, a single domain wall here. And as I'm running the simulation, I see that basically this, so plots are done in equidistant time increments. And this wall is moving really fast, right? So here the curves are all close, but this wall is moving very fast because its velocity is basically 1 over domain wall width. So in the spin dynamics, in the numerical spin dynamics simulations, we are confirming basically the analytical argument before that the velocity is inversely proportional to domain width. Okay, so here contrast is not fantastic, but basically one can see that the velocities, they are basically proportional to the domain wall width, to the two outer domain wall widths. All right, and so here basically I'm showing the same thing. This is time, this is coordinate, and initially I had this single domain wall in the middle. I nucleated another one, and it's moving quite quickly initially. And then basically this red domain shrinks, and ultimately it disappears, and you have some magnon emission here. So all kinds of interesting things are happening. So this is S dot, so this shows which spins are rotating, right? And so for a normal domain wall, this would be, the velocity would be just the same for both domain walls, so this would be straight lines. But here we have this domain moving much faster, this domain wall, and you see there is red here, so these spins are rotating much faster than these guys. Then there are some magnons emitted, and you see they're propagating back and forth, and here as well. So the situation in numerics is more complicated, but the main features are kind of there. Then this is experimental work by the group of Markus Braden from Cologne. They have done experiments with terbium-manganite where they basically reverse electric field, and on a huge time scale with a kiloseconds. So 6 kiloseconds is like 10 hours, right? You have this rather quick initial variation of polarization. This is like second harmonic intensity. And then the dynamics slows down. And we think this could be because domain walls are initially close to the surface, and then as they get deeper into the bulk, then this 1 over x kicks in, and then there is also disorder. So type 2 domain walls, they are normal. Basically, one can write simple Landau theory for them in terms of this normal plane, and well, you see there is, compared to this complicated behavior, right, where velocity is changing with time, here velocity is basically constant. Then with disorder, there is also interesting behavior. So for spin density, for charge density waves, the coercive field changes with 1/4 of the concentration. But here the critical exponent turns out to be different. So basically here we are simulating also numerically the Hamiltonian with J1, J2 competing nearest neighbor and next nearest neighbor. And then we have also the disorder implemented as a local easy axis in the plane. So basically with easy axis they are random at these different points. So the points are indicated here. This is work of Margarita Parodi also in the audience. And basically as we move the wall through the disorder, I mean, you see sometimes some steps are created, and overall the cursive, so we basically compute ultimately the cursive field as a function of the strength of disorder and its concentration. So strength of this anisotropy and the concentration of these impurities where this term is included, right? And then this basically falls on this scaling curve. And so one can think of it in the following way. So the usual argument why the disorder destroys the order in the dimensions lower than 4, one basically takes this Larkin length and starts to compare the, in terms of dimensions, the stiffness term basically and the disorder term. And then here one basically gets something like CRD minus 2a square. And here basically there is a random walk due to the impurities. So the impurities within this domain of the size of the Larkin length, they create this random walk and create basically the field of the strength RD over 2, like a random walk, right? And so when I'm equating these two factors, then I get 4 minus d here, which tells me that basically in the dimension less than 4, I will destroy the long range order. But in a spiral, I basically have a term like this, right? Number of phi square minus q square. So when the spins are rotating, they are rotating basically in one of the minima, either plus q or minus q. And when I'm expanding around with minus q, let's say, then I'm getting basic. Yeah, I'm thinking of quasi 1D, so spiral tendency in one direction and ferromagnetic exchange in the perpendicular, let's say, right? And so, so there is no Goldstone, right? It's just two minima. And so then, basically, I'm expanding in one of the minima, and that gives me a different situation, so which is called, so Natterman calls it superelasticity. So I have basically long range order in the dimension bigger than 2. Okay, then, oh, I have to wrap up, right? Okay, so it turns out, well, there are these interesting domain walls where the phazon controls things, but also for the boring ones, where there is a twist of the plane of the spiral. If you consider a situation where the plane of the domain wall is perpendicular to the k vector of the spiral, then you basically have to twist the spin rotation plane like this, right? So here basically there is k vector this way, here k vector this way, and there is a twist from one to another. And if I do that, I create an array of merons. And then the dynamics, basically, if I apply electric field, these merons dimerize, and that gives rise to the mass of the wall. So there is some interesting behavior to that. Anyway, there are interesting defects. So in the lowest energy state, the merons have to alternate their signs, but there are interesting defects appearing in the simulations. And they charge the domain wall with topological charge and give rise to the coupling between velocity of the wall and the phazon in the domains across. Anyway, so that leads to interesting dynamics. There are also interesting hedgehog defects and planar defects, all kinds of defects. That brings me to my conclusions. I hope I conveyed that there is a hope basically to switch the ordered materials not through nucleating the domains, but through rotating the potential energy surface. And that could lead to some possibilities also for applications potentially. And then in the main part of the talk, I discussed how the domain walls in spiral magnets are ferroelectric, and there is non-trivial dynamics due to twisting that's going on. Thank you very much.